blast format. Okay, we will do a standard blast database analysis. Okay, by the time it runs, we will cover what is to be studied in the blast results. Okay, blast results contain a query coverage which tells how much your sequence aligns with the database hit. It performs pairwise analysis. Okay, a higher percentage of identity means higher your results are accurate. Next it is percentage identity. How identical are the sequences covered in that region? Goal is to find a sequence which is higher than the 97% high coverage. Okay. Next it is e value, the number of hits expected by a random chance. Lower is the better, but goal is to have it at 0, but sometimes it shows as a 10 raised to 10 raised to e raised to minus 10 and all. But when it is e raised to minus 10 or 50, higher the subscript, higher better the results. Okay, let us see if the sequence, if the results are ready. Not yet. Okay, I'll show you what my I have a result sheet in my page. Okay, this is the common result page from NCBI Blast. It contains, when you look at it, the query cover, e value, and percentage identity. It is, sorry, this is a different. Okay, percentage identity, e value, and query cover. This the sequence. Just a minute. We'll look at the, yeah, we have the results here. This is the result page from, this is the result page of whatever sequence I have added. And when you look at it, it matches with Enterobacteriaceae bacterium with 100% cover and zero e value, percentage identity of 100%. This is the best match because this is the sequence I have taken. Okay, that's why it is matching. And second match is E. coli strain BH4 69 RNA gene, and the query cover is 96%, percentage identity is 82.46%, and e value of 0. For performing multiple sequence alignment, we will select top 5 to 10 sequences from this blast results, which is from the pairwise alignment. Okay, we will leave this sequence because this is the sequence I have taken for as a query. Okay, top 5, we can select this and go to downloads and download it as a faster faster sequence. Okay, by the time it downloads, we'll look at the graphical summary. Okay, select all. Yeah, this is a graphical summary. This is our query starting from 1 to the query is of 800 sequences long, and this is the top hit, which is Enterobacteriaceae bacterium. It covers 100% query sequence, 100%, 100% query cover and 100% identity. Okay, coming to next one, which is E. coli strain BH4, which covers 96% query cover and percentage identity is 82%. Okay, but when you go to below, it covers only very short length of identity. And let us look at the alignments. These are the alignments. It is a pairwise alignment. When you see, this is the query we have given, and this is the match. Let us look at the second sequence. This is the query we have given, and this is the second sequence, which shows 696 nucleotides are matching with the query, which is of 844 nucleotides, which corresponds to 82% query cover. Okay, like this, a query is matched with every single sequence of database in the database, and the result is given. Moving to the taxonomy, we will go to distance tree of results, where we can find what are the related sequences for the query we have given. When identifying an unknown bacteria, usually the blast is performed and distance tree results are considered first, and then we'll move ahead to multiple sequence alignment. Okay, fastest minimum, yes. I think it is reloading. Okay, here it is. This is the query we have given, and it matches with Enterobacteriaceae bacterium ACS. This is the actual test sequence which I have taken for as a query. So it matches with this exactly 100%, and we leave it for today. Okay, it matches with Ranctobacter. This is a node which has started, and this is the query I have given. So it matches 80% with Franconibacter helvinthiis. Okay, and it mostly matches with enterobacteria, and uncultured bacteria. Mostly it matches with enterobacteria. Okay, this is a sequence actually from the E. coli we had given. Okay, now we'll go for hands-on. Hands-on, you will be doing what you will be performing the NCVA blast. Okay, I'll just give you the sequence. I am giving you all a link. Please, please download the sequence and perform the NCBI blast, and then we'll go for your questions. Please elaborate on what is multiple sequence alignment. We'll move ahead to multiple sequence alignment in further. But first we'll go for hands-on analysis for NCBI blast. Okay, you all will be performing NCBI blast one by one. Can anyone give a hands up if it is downloadable? Yes, okay. All of you, please perform NCBA blast for the sequence I have shared. If anyone is having any difficulty, you can uh, type the message in the chat box. If all of you are done, please give me a thumbs up. Okay, many are giving a thumbs up. Yes, yes. Yes, can we move ahead? Is everyone done? Top 5 to 10 you can select. Do I have to select the uncultured bacterium? No need to select the uncultured bacterium because it is not classified and we cannot give us a specific species or identification based on what is not what is uncultured and unidentified. Yes, yes, yes. Okay, we will move ahead with the next session. That is okay. Have you all got your top 5 hits? Mostly, you should prefer the reference sequences and download the FASTA sequence. Top 5 to 10 hits you can download. You can ignore the uncultured sequence for your analysis, but for now you can for practicing you can actually select. Okay, we'll look at what is blast and multiple sequence alignment. In the blast it does mainly pairwise alignment. It means a query is compared to what all the sequences present in the nucleotide database, and the results are given. Okay, in the multiple sequence alignment we give the input of 5 to 10 sequences, and the similarity search is performed for the 5 to 10 5 to 10 sequences you have given. Okay, to find it is multiple sequence alignment is mainly done to find the conserved residues and find the structural motifs and mostly find the evolutionary relationships. Okay, for example, you have selected Enterobacteriaceae bacterium as a first sequence, and a next sequence maybe it was E. coli. You have selected next sequence Franctobacter. So we will find the evolutionary relationship between first top 5 to 10 sequences you have chosen. Okay. Moving to multiple sequence alignment, it aligns three or more sequences to the to find the homologous residues and shared patterns. Okay, it is used to compare 16S RNA sequence with the reference sequences, enabling identification of conserved sequence and variable sites. Common multiple sequence alignment tools used are Cluster W, Cluster Omega, and Mega. Okay. And moving ahead with Cluster Omega. Cluster Omega is available in web-based or command line versions is also available for example, you have thousands of sequences you want to compare. So Cluster Omega takes a maximum 4 MB of data to compare and give the results of multiple sequence alignment. In that case, you can perform using command line versions available. Okay, it generates aligned sequences, conserved patterns, and phylogenetic relationships. This is the Cluster Omega homepage, and we will move ahead to Cluster Omega. Okay, can everyone see the? Okay, is the screen visible to everyone? Yes. Okay. In the Cluster Omega, this is the homepage. I think you all don't have the link. I'll just share it in the chat box. This is the homepage of Cluster Omega, and we choose DNA as we are comparing or RNA. Maybe you can choose. You can go to select and select the sequence dump where you have downloaded the top sequences. Okay, and cluster Omega with character counts. Okay, you can give the title and submit. Okay, this is the cluster Omega result. Star means it is conserved. This is the first query we have given, we have downloaded, which is of 100% query cover and 100% identity match. Okay, which is of 800 something of length. Okay, see, look at here. From here, it is of 882 sequence length, and as we can observe, the so many sequences in between are conserved, and we move to alignment. So this is the color alignment which is shown based on color identity of the ATGC nucleotides color matching. Okay, and this is the guide tree. This is the phylogenetic tree we get, and in the phylogenetic tree we can choose whatever alignment we want. Okay, if we want a radial alignment, that also we can choose. This is the alignment summary. It shows it is based on a distance based result, which shows these four sequences are mostly similar, and this is the one uh, which is not mostly similar to these four to these four sequence microorganisms, and this is called distance based tree. That means the longer the distance, higher the evolution. Okay, result viewer, and results can be downloaded, and it can be viewed whenever you want. Okay, now all of you, can you perform? Okay. Star means usually it is conserved, and it indicates structurally and functionally important regions useful for universal primer design. For example, you are working on E. coli. Okay, I'm taking so much of E. coli as an example. We'll go for Pseudomonas. We are working on Pseudomonas, so you can choose universal. You can choose a conserved region of Pseudomonas, and you can go for specific primer designing, which is specific for specific for Pseudomonas, and which is not specific for other microorganisms. Okay, this is to do the mutation analysis, and gaps are represented by a dash. Okay, this is the basic output of cluster omega results. Okay, now all of you can perform cluster omega and give me a thumbs up when it is done. Okay. Okay. Output format. Okay. In the pasta format, the alignment is alignment results you get are in the pasta format. Okay. Usually there are similar sequences, right? Sequences are matched in the multiple sequence alignment format, and you get the faster format for all the sequences you give. Okay, clustered omega with character counts is a similarity with whatever this kind of result, where you get the similarity for conserved agents for star, and substitutions are marked by semicolon and comma. Gaps are marked by dash. Okay. Pylib usually gives the phylogenetic tree analysis, and Vienna it is I think it is a dot bracket format of results, where we can observe the structures of sequences. Okay, can all of you perform and give me a thumbs up when done? Now you all may have a doubt, like you get the phylogenetic tree in the NCBI blast results. So why do you have to perform phylogenetic analysis for multiple sequence alignment, and go to the cluster omega and get the phylogenetic tree? Can anyone answer? You get phylogenetic tree in both NCBI blast as well as cluster omega. So what is the difference? Can anyone answer? Can anyone guess? No. In the NCBI blast and cluster omega, both give the distance tree of results. Okay, it is based on evolutionary analysis, and both results are not 100% accurate, and we'll have to go to the softwares like Mega and Mega for confirming the species wise identity. Okay. Uh, in the cluster omega, we usually multiple sequence alignment is performed for top sequences. So we identify the top sequences, and mostly evolutionary data is data you get in. But in the NCBI blast, it is the overall result of whatever. I mean, you get the overall result for all the database results. It is present. Okay. When comparatively, cluster omega results are better when compared to NCBI blast. Okay, we'll go for a mini challenge. Okay, you have performed NCBI blast for an unknown 16S RNA sequence. Okay, Here are the top results. So first organism, for first sequence it is matching with is E. coli, which has 99% identity and query coverage of 95% identity and e-value of 0. And the second one is 99.5% identity and query cover of 70% and e-value of 0. The next one matching with Klebsiella pneumoniae of 98% identity, 98% carry cover, and e value of 1 to the e raised to minus 40. So, what hit would you select based on today's session? 1, 2, 3. You can type the answers in the chat box. 3. First one, E. coli. 3. You can't get the question. Okay. You have performed NCY blast and which is of query cover, which is of percentage identity 99%, 95%, and e value of 0. So the best answer is E. coli, which is of 99% identity and 95% coverage. You should look at both percentage identity, query coverage, and e value. Okay, so this is the end of my session, and this is my link. Today, you have learned how to run BLAST independently, interpret the results, and perform multiple sequence alignment and identify the unknown bacteria. Okay, so to go deeper, if you need any hands-on training, internship, or live project, CRO, or research services, you can contact me. This is my LinkedIn page. DM Bioinfo on LinkedIn for more services or any collaboration or anything you may need. Thanks for the opportunity of being a trainer for this training session. I would like to thank Afro Biolink Bioinformatics training series. So, if you have any questions, you can type in the chat box, or you can DM me on LinkedIn. Okay. Done. I have shared my LinkedIn link in the chat box. I thank Afro Biolink Bioinformatics training series. How can the output of cluster omega be used in downstream phylogenetic tree construction? The output from the cluster omega can be used in mega, which is specifically designed for phylogenetic analysis, and maybe in the coming training sessions or uh, the coming training session, or you may learn independently. We can go for phylogenetic tree analysis using mega. It gives the specific analysis for specifically it is designed for phylogenetic tree analysis. Okay, you can use mega for downstream analysis. Okay, any questions? Is it that the very low e value doesn't matter in the selection of? See, you need to look at all the three. Okay, when we look at e raised to 40 doesn't mean 0. Okay, it doesn't mean it is 0. We'll have to look at the e value also, that is right. E raised to minus 40 doesn't mean it is 0. 0 here means e raised to minus 180, which is equal to which is almost equal to 0. Okay. When it is e raised to minus 40 and 0, you choose 0. When it is e raised to 40, minus 40 and e raised to minus 50, you choose the one with e raised to minus 50. Okay. Is it possible to use split tree for phylogenetic tree analysis? See, you can use whatever tools you want, but Mega is specifically designed for phylogenetic tree analysis, and it is widely used and it is well documented. So it is the gold standard for phylogenetic tree analysis. Okay. So if questions are done, I'll conclude my session here. Over to you.